Very early on in our study of algebra, we learn about the Cartesian coordinate system. This system lets me describe the location of any point in space simply by assigning an arbitrary point in space as the origin, and then describing the location of this point as a distance away from the origin, first to the right of the origin and then up. In other words, I'm going to go to the right 2 units and up 4 units. I could go up and then right, but we've agreed on a convention that we'll go right first and then up. So the coordinates of this point are 2, 4, because I went from the origin right 2 and up 4. I can also describe the location of points in other quadrants simply by going left instead of right, down instead of up, and so on. And that's pretty familiar. That's pretty comfortable. We've been working with the Cartesian coordinate system for quite a while now. But that's not the only way to describe the location of a point. Here's another one. What if, instead of going from the origin to the right and then up, or to the right and then down, or to the left and then down, for example, what if instead I went out a certain distance and then around, as though I were tracing an angle? Well, that's all the polar coordinate system is. If I want to describe the location of this point in that system, then I need to know how long that line segment is and how big that angle is. Coordinates in the polar coordinate system are described as r first and then theta. It's not hard to imagine that this point is on a circle and that circle has a radius of r. And that's exactly what we're talking about when we use r for the first coordinate in a polar coordinate system. Theta is equally obvious, I think. It's the angle from standard position that you go around until you get to this radius, until you get to this line segment. So while this point right here and this point right here appear to be at about the same position, this distance away and this far around, or this far up and this far out and this far up, they're at about the same location on the screen, or at least in relation to the origin in each case. But I've used 2 different coordinate systems to describe the location of that point. And that's what this section is about. This is how we define polar coordinates. There are a couple of things you should know. One is that you can have a negative radius. For example, if I had an angle, let's put one here. I can describe this point 2 different ways. One is that I can say the radius is a positive value and the angle is a large angle. Or I can say that the radius is negative whatever this radius would have been. In other words, let's say this angle right here is pi over 6. I can describe this point right here as, oh, well, let me give you a radius too. How about 5? So that says that the line segment here, from the origin to this point right here, has a length of 5. And this one here also has a length of 5. I can describe this 2 different ways. This point right here, I can describe it 2 different ways. I can either describe it as a radius of 5, but in the opposite direction, in which case my radius is negative, and then the angle is pi over 6. To find the location of, if I'm just given these coordinates, what I would do is I would say go out pi over 6, and then instead of going this way 5 units, go back 5 units. The other way I could describe it would be to say that my radius is 5, but positive, so now I'm starting here and going in this direction right from the beginning. But to get there, I have to go around this angle. and that's 7 pi over 6. So I can either have a positive radius with a larger angle or a negative radius, in this case with a smaller angle. There's actually another way to describe it. Let's let the radius stay 5, positive 5, but instead of going from here around in this direction, let's take our angle in the opposite direction. So 5, comma, the angle is negative 5 pi over 6 is another way to describe the location of this point on the plane. Going back to the Cartesian coordinate system, we call this point here the origin. It has coordinates 0, 0, because I'm going to go right or left 0 and up or down 0 to get to that point from this location. This point on the polar coordinate system also has coordinates 0, 0, but for a different reason. Here we're going to go out 0 and around 0. My r is 0, my radius, and my angle also is 0. So the coordinates are the same, but for different reasons. And this point, in this context, we call this point the pole, hence polar coordinates. In the Cartesian coordinate system, we tend to call this axis the x-axis, the horizontal axis, and the vertical axis the y-axis. In the polar coordinate system, we call the x-axis, or the horizontal axis, the polar axis. There is no name for the vertical axis because we don't actually need it. All we need is a horizontal axis and a pole. From there, I can say go out this far and around this many radians. Go out this far and around this many radians. Take the radius to be whatever the first coordinate in the pair is. In this case, it's 5, so I'll go out 5, and then go around negative 5 pi over 6. In fact, we don't really even need the negative horizontal axis. We can literally use just the positive, what we were calling the positive x-axis. Everything there from there is just find an angle and find a radius. Or you're given a radius and you're given an angle. The truth of the matter is we tend to use a different set of coordinate axes for graphing polar coordinates and for graphing graphs of polar coordinates because it helps us keep things straight, right? In this system, we don't really need graph paper that has lots of little subdivisions in it, but if we have that, we can find it easier to be more accurate when we're graphing. If we were to graph the point 1.3, comma 0.9, we'd be able to find that more accurately. That's about there. If we had these subdivisions on our graph paper. So we have a special kind of graph paper called a polar graph paper or polar coordinate graph paper that we use to help us keep things straight. It'll help us decide exactly how far out to go. What is a radius of 1 or what is a radius of 3? And exactly where is that angle that we're looking for? So on the next slide, I'm going to show you what that graph paper looks like, and we'll talk about how to use it. Here's what the graph paper looks like. On page 588 of your textbook, right down at the very bottom of that page, example 1 lists 4 points in polar coordinates. I'm going to show you how to plot those points on this system. Let me start by writing out what the points are that they give you. And then we'll just go through each one of these one at a time. We'll start with letter A, number A. The point is 1, 3 pi over 4. Now, I actually find it easier, even though these are in the order r, theta, I actually find it easier to go find the angle first. What I want to do is go out 1 and then around 3 pi over 4. But if I knew where on the circle I was headed, then once I got there, I could start at the origin and go out that far, right? So let's go find the angle 3 pi over 4. This is the angle 0. This is looks just like the unit circle, right? I've got all my pi over 6, pi over 4, pi over 3, pi over 2, and so on, all the way around the circle. This one's really nice because it actually has pi over 12. These are nice even subdivisions of the circle. So pi over 6 and pi over 4, pi over 3 and pi over 2, those are our common angles that we've been working with all quarter. We want 3 pi over 4 though. If this is 0, and this is 1 pi over 4, 2 pi over 4 is pi over 2, here's 3 pi over 4. And of course, it's also labeled, so we can find it quite easily. Now that I know that's the direction I'm going to go in, I'm going to trace along this line just as a guide. I wouldn't normally include this line, but I'm going to do it this time just so that you know where we're headed. So remember that I'm doing my theta first. I'm thinking that starting here, I'm going to go around 3 pi over 4. But the other value here tells me how far out to go. And just as with regular Cartesian graph paper, the scale is very important here. There's no scale listed on this circle. So I could say that this was 1. How many tick marks do I have there? 1, 2, 3, 4, 5. So if I get 5 marks to every 1, 1, 2, 3, 4, 5, then that would be a 1 right there. That's 1. And 1, 2, 3, 4, 5, that would be 2. 1, 2, 3, 4, 5, that would be 3. And I can do that if I want to. I can just change the scale in the same way as I was allowed to change the scale in the Cartesian system. Just make it big enough or small enough to suit whatever I was trying to plot. So now that I know what 1 is, what I'm essentially saying is that I want to be out along this line somewhere and somewhere on this circle. This is the circle with radius 1. I'm not going to make you watch me do the whole thing. There's the circle. Where those two curves intersect right here is the point 1, 3 pi over 4 in polar coordinates. From here, I've gone out a radius of 1, having labeled it 1, having decided that's what 1 was going to be. I defined that to be the radius of 1. And I've gone around 3 pi over 4. So this point right here has coordinates 1, 3 pi over 4. Okay, let's do another one. Let's look at letter B here. 3, negative pi over 6. Now, I could go out my radius 3 first, and then around pi over 6. Well, it's negative pi over 6, isn't it? So it's down here. Negative pi over 6. And that you're welcome to do it that way. If you know what your radius is, and then you can follow the circle around to a distance of pi over 6 radians away from that point, then you're certainly welcome to do it that way. That's where that point would be right there. That is 3, negative pi over 6. But I just tend to find it easier to find my angle first. I know that that's going to be, that line right there is negative pi over 6. And then once I found that line, that's like my goal. I know I'm going to be heading in this direction. I want to land there, and I want to come around the circle with radius 3 until I get there. Okay, so that's 3, negative pi over 6. A positive radius, but a negative angle. All right, let's do 3, 3 pi. So I'm going to find my angle first, which means starting here, I'm going in this direction because it's a positive angle. I'm going to go around pi, 2 pi, 3 pi. So my angle this time is this line right here. It's coterminal with pi, and if you caught that, you're welcome to use that fact, right? We're going in the same direction as we would be if this had been 3, pi, but it's because 3 pi is coterminal with that. Now I'm going to find the circle with radius 3. It's this circle right here. So if I'll trace that along, I get to here, and I'm going to find the place where these two curves intersect, and that is where my point is. That is the point with coordinates 3, 3 pi. All right, my last example here. I'm not color coordinating my work here very, very well. I've highlighted this one in blue. It makes it look like it goes with this point, but it doesn't. This one has coordinates negative 4 pi over 4. So if I find my angle first, pi over 4 is here. So I'll be going along this line, except that this time my radius is negative. So instead of traveling along that line, I'm actually going to be traveling along this line. The angle is positive pi over 4, but the radius is negative. And the radius is negative 4. So let me see if I can figure out what negative 4 would look like. So I've got 1, there's 2, 2, 3, 4, 5. There's 3. So they're about that distance. So 4 is probably about there. So this point, we'll go with green this time. This point right here has coordinates negative 4, comma, pi over 4. Now, I've given you a set of coordinates and asked you to find the point that goes with that coordinate, that set of coordinates. I've given you another point and asked you to find that point. What if I give you a point? Can you tell me what the coordinates are? Let's put a point right here. What are the coordinates of that point? Well, one way you could find out is to figure out what circle it's on. If you trace that circle around, trace this curve around to where I put the scale, that has a radius of 2. That circle has a radius of 2. So my coordinates r comma theta will be 2 comma something, because I'm out 2 units from the origin, from the pole. Okay, and then from 0, how far around did I have to go? Well, you can just line that up with what the label is for that angle here. That's pi over 3. So the coordinates of that point are 2 comma pi over 3. Well, that's pretty much it for polar coordinates. There's a lot we can do with them, but as far as their definition, that's really all we need to do. We've talked about both positive and negative radii and positive and negative angles. And we've talked about coterminal angles too. So in the next video, we're going to be looking at the relationship between polar coordinates and rectangular coordinates in a way that we haven't really talked about yet.